Okay, so in this video we want to find the inverse Laplace transform of this function f of s, which is 5s minus 10 over s squared minus 3s minus 4. And I'm going to assume you've got this table of common Laplace transforms in front of you, and you're looking at the right column of that table and trying to identify which of those expressions in the right column does this most look like. And it really doesn't look like any of them. But here's something that's always worth trying, and that is if we can factor the denominator, then that's going to have a nice fact. So in this case, we can factor the denominator. So I could write the top, that's 5s minus 10, and maybe we can even reduce some common terms. So looking at the denominator, I can write that as, for example, s minus 4 times s plus 1. And on top, that's not going to cancel out any factors in the numerator of this fraction. But because the bottom does factor, then maybe I can rewrite this fraction as a sum of two fractions. So maybe I can do some partial fraction decomposition on this so that I can find values for a and b such that when I do add these two together, I wind up getting back the fraction that we started with. So when you can factor the denominator with these problems, that's always a really good way to go, because up here we have the result of what is the Laplace transform of e to the at. That would give me 1 over s minus a. So I know how to calculate the Laplace transform of things like this. So let's go through the partial fraction decomposition step here. So what I would do if I wanted to add these two together, well, I would multiply the a over s minus 4 times s plus 1 on the top and on the bottom. And I'm going to multiply the second fraction by s minus 4 over s minus 4, and that puts it all over this common denominator. And then we can group our terms. So we have an a plus b being multiplied by s, and the constant terms would give me, I have an a and a minus 4b. And all of that is now over s squared minus 3s minus 4. So I need to find values of a and b so that a plus b gives me the 5 in front of the s, and the a minus 4b gives me the minus 10 over here. So I have a system of two equations now. A plus b is equal to 5, and I have a second equation, a minus 4b is equal to minus 10. And I want to solve this. So for example, if I subtract the second equation from the first equation, the a's would cancel, and I get 5b is equal to 15. So b is equal to 3, which therefore tells us that a is equal to 2. So now if I want to calculate the inverse Laplace transform of our original function, that equals the inverse Laplace transform of 2, which was our a value, over s minus 4, plus b, which was 3, over s plus 1. And now we can use the linearity of the inverse Laplace transform to therefore say this is going to equal 2, can be pulled out, times the inverse Laplace transform of 1 over s minus 4. And then for the second one, we can pull out the 3 and calculate the inverse Laplace transform of 1 over s plus 1. And then, using the shortcut that we identified, at the top, up here, we can see that this is equal to this, where a is 4. So for that first one, we would get e to the 4t. And for the other term here, our a value is -1 from this piece over here. So that's going to give us 3 times e to the -1 times t. So this would be the resulting inverse Laplace transform of the function that we started with. So really, the main point here was we had to use fraction decomposition in order to take this original fraction and write it as a sum of two fractions, each of which we can find the inverse Laplace transform pretty directly from the table.